Hello students, welcome to this lecture on complex numbers and quadratic equations theory. In this lecture, we will cover NCERT section 4.1, 4.2, 4.3 and 4.3.1 to 4.3.4. So let's get started. This is disclaimer. Now, let's look at index of today's lecture. So in this lecture, first we will discuss NCERT section 4.1 introduction. So there we will introduce complex numbers and quadratic equations. So we will start with an introduction to this chapter. Then we will look at section 4.2, which introduces complex numbers. Complex numbers are numbers that have both real part and imaginary part, written in the form a plus iota times b, where a and b are real numbers. Then we will solve an example. Next, we will move to the section 4.3, which covers the algebra of complex numbers. So in this section, we will know how we can add to complex numbers, how we can subtract to complex numbers, and how we can multiply and divide complex numbers. Okay. So here in the section 4.3.1, we will talk about the addition of two complex numbers. If we have two complex numbers, z1 is a plus iota b and z2 is c plus iota d, then how we can add z1 and z2? About that, we will discuss in 4.3.1 section. After that, in section 4.3.2, we will discuss about the difference of two complex numbers. Next, in section 4.3.3, we will discuss how to multiply two complex numbers. Finally, in section 4.3.4, we will discuss the division of two complex numbers. So how we can divide two complex numbers, we will discuss in 4.3.4. So let's start today's first topic, introduction. So let's start by looking at the equation x square plus 1 equal to 0. Notice that if we try to solve this using real numbers, we run into a problem. That's because the square of the any real number is always 0 or positive. So x square can never be negative. This means x square plus 1 equal to 0 has no solution in the real number system. So that is why we introduce a new number, that is complex number. So we need to make our number system bigger than real number system. Okay. So in other words, the real numbers are not enough for us to solve every equation we might encounter that we have seen in equation x square plus 1 equal to 0. In this case, there is no real solution because x square is equal to minus 1 is not possible for any real number x. Okay. So by expanding our number system, we can start to solve equations that were previously unsolvable. So this means we introduce new types of numbers that allow us to find solutions where none existed before. So this is a big step in mathematics because it opens up a whole new world of possibilities. Okay. So historically, the mathematician Euler was the first to use the symbol iota, okay, which is called iota. So this symbol is called iota to represent the value of square root of minus 1. That means iota is defined as the square root of -1. This was a major breakthrough because it gave us a way to talk about and work with solution to the equations like x square plus 1 equal to 0. With this new idea, mathematicians developed the system of complex numbers. So complex numbers allow us to solve any algebraic equation, not just like ons with real solutions. So try introducing that is called iota, okay, and complex numbers. So we have made our mathematical toolkit much more powerful. So we will begin by understanding what a complex number is, so how it's written, and what its different parts mean. Okay, so let's look at the formal definition of complex numbers. A complex number is any number that can be written in the form a plus iota b, where both a and b are real numbers. Here, iota is the imaginary unit, which is defined as the square root of minus 1. So, this form allows us to the square root of minus 1. So, this form allows us to represent the numbers that cannot be shown on the real number line alone. Okay. So, we usually use the letter z to represent a complex number. So, we write z equal to a plus iota times b. This notation helps us keep track of both the real and imaginary parts in one expression. Okay, so let's break down what each part means. In the expression z equal to a plus iota b, a is called the real part of z and b is called imaginary part of z. Okay, so we write a as real of z. For example, if z equal to 3 plus 4 iota, then the real part of z is 3. Okay, so it's part of the complex numbers that doesn't involve iota. The value b in z equal to a plus iota b is called the imaginary part of z, and we write this as im of z. Okay, imaginary of z. Okay, and for example, if z equal to 3 plus 4 iota, then the imaginary part of z is 4. So remember, the imaginary part is just the number multiplying by iota, not including the iota itself. All complex numbers together form a set, which we call C. So whenever you see the symbol C, it means the set of all possible complex numbers. So this set includes every number that can be written as a plus iota b, where a and b are real numbers. Let's take an example to make this clearer. Suppose we have the complex numbers z equal to 2 plus 5 times iota. So we will find both the real part and the imaginary part of this number. So this will help us see how the definition works in practice. So let's see how to solve this question. So given here z equal to 2 plus 5 times iota. So let's compare with the general form of complex number z equal to a plus iota b. So by matching up the terms, we can identify the values of a and b for this specific example. So now comparing z equal to 2 plus 5 iota with z equal to a plus iota b, we get a equal to real part of z equal to 2. Here b equal to imaginary part of z is 5. Now, let's look at some special cases in complex numbers. So, these cases help us understand how the real and imaginary parts of a complex numbers can affect its clarification. So, we will break down each case step by step. So, pay close attention to how the equations change as we go. First, let's recall the general form of a complex number. So, Z equal to A plus iota B, where A and B are both real numbers. Here, A is called the real part of the Z and B is the imaginary part. So, this form is the foundation for all the special cases we will discuss. Now, let's see what happens if the real part A is 0. So, if A is 0, then Z equal to iota times B. So, this means the complex number has no real part and only an imaginary part. So, we call it a purely imaginary number. Let's take an example to make this clearer. Suppose we have the complex numbers Z equal to 3 times iota. Our goal is to find both the imaginary part and the real part of Z. So, we will do this step by step. Given that Z equal to 3 times iota, so let's write down in general form of complex number Z equal to A plus iota B. So, this will help us identify the real and imaginary parts directly. So, we can rewrite as Z equal to 0 plus 3 times iota. Now, let's compare Z equal to 0 plus 3 iota with Z equal to A plus iota times B. We get A equal to 0 and B equal to 3. So, we can observe that Z equal to 3 times iota is a purely imaginary number as A equal to 0. Now, let's look at some special cases involving complex numbers. So, here let's consider the case when B equals 0. Remember, a complex number is written as Z equal to A plus iota B, where A is the real part and B is the imaginary part. If B is 0, then Z is equal to A, which means the number is purely real with no imaginary component at all. Let's look at an example to make this clearer. Suppose we have the complex number Z equal to 7. We will find both the real part and the imaginary part of Z. See how it fits the form Z equal to A plus iota B. Given that Z equal to 7, so let's write down what we know. Here Z is just 7 and we want to identify its real and imaginary parts by comparing it to the standard form of a complex numbers. So, we can rewrite Z equal to 7 as Z equal to 7 plus iota times 0. This makes it clear that the real part is 7 and the imaginary part is 0. Now, comparing Z equal to 7 plus iota times 0 with the general form Z equal to A plus iota times B. So, we see that A equal to 7 and B equal to 0. We can observe that Z equal to 7 is a purely real numbers and as B equal to 0. we observe that when b equal to 0 and z equal to a, we are really just talking about real numbers. This means the set of all real numbers, which we call R, is actually a subset of the set of complex numbers, which we call C. So every real number is also a complex number with 0 imaginary part. Now we will discuss about equality of complex numbers. This is an important concept in understanding how to compare and work with complex numbers in mathematics. So we will see how it determines if two complex numbers are equal by looking at their real and imaginary parts. So let's start by stating the rule. Two complex numbers, say z1 is a plus iota b and z2 is c plus iota times d, and z1 and z2, these two complex numbers, are equal if and only if their corresponding real and imaginary parts are equal. Now, to put this more formally, if z1 equals z2, then the real part of z1 must equal the real part of z2 and the imaginary part of z1 must equal the imaginary part of z2. So if z1 equal to z2, then real part of z1 equal to real part of z2 and imaginary part of z1 equal to imaginary part of z2. Now let's write out with variables. If a plus iota times b equals c plus iota times d, then a must equal c and b must equal d. Now let's look at an example to make this clearer. So we will check if the complex numbers z1 equal to 5 plus 2 iota and z2 is equal to 5 plus 2 iota are equal. This will help us apply the rule we just learned. So given that z1 equal to 5 plus 2 iota and z2 equal to 5 plus 2 iota. So we will now compare their real and imaginary parts step by step. So here we can see that real part of z1 is 5 and imaginary part of z1 is 2. Real part of z2 is 5 and imaginary part of z2 is 2. Since real part of z1 equal to real part of z2 and imaginary part of z1 equal to imaginary part of z2. So we can conclude that z1 equal to z2. Now we will look at an example. So we are given the equation 4 times x plus iota times 3x minus y is equal to 3 plus iota times minus 6, where x and y are real numbers. Then we have to find the values of x and y. So first of all, try it yourself. How would you approach this example? Let's solve this example step by step. To solve this, remember a key property of complex numbers. If a plus iota b is equal to c plus iota times d, then the real parts must be equal, that is a equal to c, and the imaginary parts must be equal, that is b equal to d. Now let's write down the equation we are working with, that is 4x plus iota times 3x minus y equal to 3 plus iota times minus 6. First, let's equate the real parts and real parts of both sides. So the real part on the left is 4x and on the right it is 3. So we write 4 times x equal to 3. So this gives us our first equation to solve for x. Now let's solve for x. So we have 4x equal to 3. It implies x is equal to 3 by 4. Next, let's equate the imaginary parts. On the left, the imaginary part is 3x minus y, and on the right, it is minus 6. So we set up the equation 3x minus y equal to minus 6. So this is our second equation. We will substitute the value of x and then we will find the value of y. Let's substitute x equal to 3 by 4 into the equation 3x minus y equal to minus 6. So this gives us 3 times 3 upon 4 minus y equal to minus 6. Now let's simplify the equation. 3 times 3 divided by 4 is 9 divided by 4. So we have 9 by 4 minus y equal to minus 6. Let's simplify further. So we will obtain y equal to 9 by 4 plus 6. And further if we simplify, then we will ultimately get y equal to 33 by 4. Therefore, x is equal to 3 by 4 and y is equal to 33 divided by 4. So I hope this example is clear to all of you. Now, we will discuss algebra of complex numbers. So here in this section, we will know how to add two complex numbers, how to multiply two complex numbers, how to subtract two complex numbers, and how to divide two complex numbers. Okay, so let's start to know addition of two complex numbers. Then we will discuss difference of two complex numbers. Then we will discuss multiplication of two complex numbers. Then we will discuss division of two complex numbers. So these are some algebraic operation of complex numbers. So let's start with addition of two complex numbers. This is a fundamental operation in complex numbers and you should understand it very carefully. So let's define our two complex numbers. So we will call them Z1 and Z2, where Z1 equals A plus iota times B and Z2 equals C plus iota times D. Here, A and C are real numbers and B and D are the imaginary parts of the number. Now, let's see how to add these two complex numbers. The sum Z1 plus Z2 is written as A plus iota times B plus C plus iota times D. When we add them, we combine the real parts and the imaginary parts separately. So the real part is A plus C and the imaginary part will become B plus D. So Z1 plus Z2 will become A plus C plus iota times B plus D. So this is the standard way to add complex numbers. So let's look at an example to make this clearer. So suppose Z1 is 2 plus 3 times iota and Z2 is minus 1 plus 5 times iota, and then we have to find Z1 plus Z2. So let's solve this example step by step. Given that Z1 equal to 2 plus 3 iota and Z2 is equal to minus 1 plus 5 times iota. So we will use these values in our addition formula. Remember, if Z1 equals A plus iota times B and Z2 equals C plus iota times D, then Z1 plus Z2 equals A plus C plus iota times b plus d. Now let's substitute the real part of Z1 and imaginary part of Z1 and real part of Z2 and imaginary part of Z2 in the formula of addition. So then Z1 plus Z2, this is equal to 2 plus minus 1 plus iota times 3 plus 5. This is equal to 1 plus 8 times iota. Therefore, Z1 plus Z2 is equal to 1 plus 8 times iota. Let's look at the properties of addition for complex numbers. So these properties help us understand how complex numbers behave when we add them together. So just like with real numbers. So we will go through each property one by one and see why they are important. So first we have the closure law. This means if we add any two complex numbers, the result is always another complex number. Then the second property is commutative law. This property tells us that order in which we add complex numbers doesn't matter. Then we will look at associative law. So this law says that when we adding three complex numbers, the grouping doesn't affect the result. Then the next property is existence of an additive identity. This means there is a special complex numbers called the additive identity, which is 0 plus 0 iota, that doesn't change any complex numbers when added. Finally, we have the existence of additive inverse. So let's start by looking at one of the fundamental properties of complex numbers, the closure law. The sum of two complex numbers is also a complex number. Okay, this means the set of complex numbers is closed under addition. No matter which two you pick, their sum is still in the set. To put this formally, if Z1 and Z2 are both complex numbers, then Z1 plus Z2 is also a complex number. Let's look at an example to clear this topic. So suppose we have two complex numbers, Z1 equals 3 plus 2 iota and Z2 equals 1 plus 1 minus 4 times iota. So we will use these numbers to demonstrate the closure law for addition. Let's solve this example step by step. So given that Z1 equal to 3 plus 2 iota and Z2 equal to 1 minus 4 times iota. We know that if Z1 equal to A plus iota times B and Z2 equal to C plus iota times D, then Z1 plus Z2 is equal to A plus C plus iota times B plus D. Now, let's substitute our values. So, Z1 plus Z2 equals 3 plus 1 plus iota times 2 minus 4 equals 4 minus 2 times iota. Notice that 4 minus 2 times iota is also in the form A plus iota times B, where A is 4 and B is negative 2. This means our result is also a complex numbers. So just like the numbers we started with. So this example tells us that when you add two complex numbers, you will get always another complex number. So the sum 4 minus 2 iota is indeed another complex number. I hope it is clear to all of you. Now we are looking at the commutative law for complex numbers. So for any two complex numbers, let's call them Z1 and Z2. The commutative law says that Z1 plus Z2 equals Z2 plus Z1. In other words, if we add Z1 to Z2 or Z2 to Z1, you get the same result. So this means that no matter which complex numbers you start with when adding, the total sum will always be the same. So Z1 plus Z2 gives us the same number as Z2 plus Z1. The order doesn't change the sum. So let's look at a specific example to see this law in action. Suppose we have two complex numbers, Z1 equals 1 plus 5 times iota and Z2 equals 3 minus 2 times iota. We will use this to show how the commutative law works for addition. So let's solve this question. Given that Z1 equals 1 plus 5 times iota and Z2 equals 3 minus 2 times iota. We know that if Z1 equals A plus iota times B and Z2 equals C plus iota times D, then Z1 plus Z2 equals A plus C plus iota times B plus D. Now, Z1 plus Z2 equals 1 plus 3 plus iota times 5 minus 2 equals 4 plus 3 times iota. Also, Z2 plus Z1 equals 3 plus 1 plus iota times minus 2 plus 5 equals 4 plus 3 times iota. The final result 4 plus 3 iota is same in both cases. This example shows the order of the adding complex numbers doesn't change the sum. I hope this property is clear to all of you. Now, we will look at associative law for complex numbers. For any three complex numbers, which we will call Z1, Z2 and Z3. So the associative law applies. This means we can add them in any order and the sum will be the same. So here is the associative law written as an equation. Z1 plus Z2 plus Z3 equals Z1 plus Z2 plus Z3. Notice that the grouping changes, but the numbers themselves and the operation of addition stay the same. So this is what makes addition associative. This means that when we are adding three or more complex numbers, we can choose any two or add them, then add the third one to that result. Okay, so the answer will always be the same, no matter how we always start with which number. Okay, so this property makes calculations easier and more flexible. So let's look at an example. So we will use the complex number Z1 equal to 1 plus 2 times iota and Z2 equal to 3 minus iota and Z3 equal to minus 2 plus 4 iota. Then we will show as these numbers hold the associative law of addition. So let's see solution. So we have Z1 is equal to 1 plus 2 times iota, Z2 equals 3 minus iota and Z3 equals minus 2 plus 4 times iota. So first we will show that Z1 plus Z2 plus Z3 equals Z1 plus bracket Z2 plus Z3. So we know that if Z1 is equal to A plus iota B and Z2 equals C plus iota D, then Z1 plus Z2 equals A plus C plus iota times B plus D. Now first add Z1 and Z2. So Z1 plus Z2 equal to 1 plus 3 plus 2 minus 1 times iota, that is 4 plus iota. Now add Z3 to Z1 plus Z2. So Z1 plus Z2 plus Z3 equal to 4 plus iota minus 2 plus 4 times iota. This is equal to 4 minus 2 plus 1 plus 4 times iota. This is 2 plus 5 times iota. So LHS equal to 2 plus 5 times iota. Now first add Z2 and Z3. Z2 plus Z3 equal to 3 minus iota plus minus 2 plus 4 iota. This is 3 minus 2 plus minus 1 plus 4 iota. This is 1 plus 3 times iota. Now add Z1 to Z2 plus Z3. So Z1 plus Z2 plus Z3 equal to 1 plus 2 iota plus 1 plus 3 iota. This is equals 1 plus 1 plus 2 plus 3 times iota. This is 2 plus 5 times iota. So RHS equals 2 plus 5 times iota. Since LHS equals RHS equals to 2 plus 5 times iota. Thus we have successfully solved the associative law of addition. Now we are going to discuss an important property of complex number, the existence of the additive identity. So this is a fundamental concept in mathematics, and it means that there is a special number called the additive identity, which you can add to any complex numbers without changing its value. There exists a complex number written as 0 plus iota times 0, which we simplify call 0. So this number is known as the additive identity of the 0 complex number. For every complex number Z, adding this 0 complex number leaves Z unchanged. So let's look at what this means in practice. So here is the key equation, Z plus 0 equal to Z. So this means that if we take any complex number Z and add 0 to it, you get back the same number Z. So if you add the number 0, which in complex number is 0 plus 0 times iota, to any complex number Z, the result is still Z. Let's take an example to make this clearer. Suppose we have the complex numbers Z equal to 7 minus 3 times iota. Then show the existence of the additive identity. So let's solve this question. So we have given that Z equal to 7 minus 3 times iota. And we know that if Z1 equal to A plus iota times B and Z2 equals C plus iota times D, then Z1 plus Z2 equals A plus C plus iota times B plus D. Now let's add 7 minus 3 iota plus 0 plus 0 iota. Okay. So Z plus 0 equal to 7 minus 3 iota plus 0 plus 0 iota. This is equal to 7 plus 0 plus iota times minus 3 plus 0 equals 7 minus 3 iota. Notice that the result is still 7 minus 3 iota, which is exactly our original complex numbers Z. This confirms that adding the 0 complex numbers leaves any complex number unchanged. So this example clearly shows that adding 0 to a complex numbers does not change the complex number. So this is why 0 plus 0 times iota is called the additive identity for complex number. Now we are going to discuss an important property of complex number, the existence of additive inverse. So this property tells us that for every complex number there is another complex number that when added to the original numbers gives us 0. So let's see how this works step by step. So for every complex number Z equals A plus iota B, there is another complex number written as minus A plus iota times minus B, which we call the additive inverse or negative of Z. Notice that we add Z and its additive inverse minus Z, we get 0. In other words, Z plus minus Z equals 0. So for every complex number Z, there always exists another complex number called its additive inverse, and we write it as minus Z. Let's look at an example to make this clearer. Suppose we have the complex number Z equal to 5 plus 8 times iota. Then we will show how to find the additive inverse. So let's solve this example step by step. So given that z equal to 5 plus iota 8 times iota. So to find the additive inverse, which we call minus z. So we negate both the real and imaginary parts. That means we take minus 5 for the real part and minus 8 for the imaginary part. So minus z equals minus 5 times 5 minus 5 plus 8 times iota. This is minus 5 minus 8 times iota. This is the additive inverse of z. So if we add now 5 plus 8 times iota and minus 5 minus 8 times iota, then we said we should get 0. So we know that if z1 equal to a plus iota times b and z2 equals c plus iota times d, then z1 plus z2 equals a plus c plus iota times b plus d. Now let's add z and its additive inverse minus z. So z plus minus z equals 5 plus minus 5 plus 8 plus minus 8 times iota. It implies z plus minus z equals 5 minus 5 plus 8 minus 8 times iota. So it implies z plus minus z equals 0. So as you can see, adding z and its inverse additive inverse minus z gives us 0. So the example shows the additive inverse property for complex numbers. Now we will discuss how to take a difference of two complex numbers. Okay, so this is an important operation in complex number. So just like addition, so we will see how to subtract one complex number from another and what the result looks like. So given two complex numbers z1 equals a plus iota times b and z2 equals c plus iota times d, then the difference z1 minus z2 is defined as z1 minus z2 equals z1 plus minus z2. So z1 minus z2 equals a plus iota times b minus c plus iota times d equals a minus c plus iota times b minus d. Therefore, z1 minus z2 equals a minus c plus iota times b minus d. Let's look at an example to make this clearer. Suppose we have z1 equal to z6 plus 3 times iota and z2 equals 2 minus iota. Then we have to find z1 minus z2. So let's solve this example. So given that z1 equals 6 plus 3 iota and z2 equals 2 minus iota. So we know that if z1 equals a plus iota b and z2 equals c plus iota times d, then z1 minus z2 equals a minus c plus iota times b minus d. So now z1 minus z2 equals 6 minus 2 plus iota times 3 minus of minus 1 equals 4 plus 4 times iota. Therefore, z1 minus z2 equals 4 plus 4 times iota. Now we are going to discuss how to multiply two complex numbers. So this is the another important operation in complex number, and we will know how to multiply two complex number here. So let's start by considering two complex numbers. z1 equals a plus iota times b and z2 equals c plus iota times d. Then the product z1 into z2 is defined as z1 times z2 equals to ac minus bd plus iota times ad plus bc. So now let's break down how this formula comes out. So we will go through the multiplication step by step so you can see where each part of the result comes from. So z1 times z2 equals a plus iota times b times c plus iota times d. Expanding this, we get a times c plus iota times d plus iota b times c plus iota times d. Now let's multiply out each term and it will give us a times c plus iota times a plus d plus iota times b plus c, b into c plus iota square times b times d. Remember that iota square equals minus 1. So iota square times bd is minus bd. So now let's group the real and imaginary parts. So z1 times z2 equals ac plus iota times ad plus bc minus bd. This is equal to ac minus bd plus iota times ad plus bc. Therefore, z1 multiplied with z2 equals ac minus bd plus iota times ad plus bc. Let's look at an example. For the complex numbers, z1 equals 3 plus 2 iota and z2 equals 1 plus 4 times iota. Then find z1 times z2. Given that z1 equals 3 plus 2 iota and z2 equals 1 plus 4 times iota. So we know that if z1 equals a plus iota times b and z2 equals c plus iota times d, then z1 times z2 equals ac minus bd plus iota times ad plus bc. Now let's substitute the values. We get z1 times z2 equals 3 times 1 minus 2 times 4 plus iota times 3 times 4 plus 2 times 1 equals minus 5 plus 14 times iota. Therefore, z1 times z2 equals minus 5 plus 14 times iota. Now, we will discuss the properties of multiplication for complex numbers. So, these properties are fundamental because they help us understand how complex numbers behave when we multiply them. So, the multiplication of complex numbers satisfy the following properties. First property is the closure law. The second property is commutative law. The third property is the associative law. Fourth property is the existence of multiplicative identity. Then fifth property is the existence of multiplicative inverse. Then sixth property is the distributive law. So let's start by looking at one of the fundamental properties of complex numbers, the closure law. So this law is important because it helps us what happens when we multiply two complex numbers together. So the product of two complex numbers is a complex number. If z1 and z2 are both complex numbers, then their product z1 times z2 is also a complex number. It means if we take any two complex numbers z1 and z2 and multiply them, then the result z1 times z2 will always the another complex number. Let's look at an example. For the complex numbers z1 equals 2 plus 3 iota and z2 equals 1 minus 4 times iota, so the closure law of multiplication. So given that z1 equals 2 plus 3 iota and z2 equals 1 minus 4 times iota. So we know that if z1 equals a plus iota times b and z2 equals c plus iota times d, then z1 times z2 equals ac minus bd plus iota times ad plus bc. Now z1 times z2 equals 2 times 1 minus 3 times minus 4 plus iota times 2 times minus 4 plus 3 times 1 equals 14 minus 5 times iota. Therefore, z1 times z2 equals 14 minus 5 times iota, which is also a complex number. So this example shows the closure law of multiplication. Then we will look at the commutative law for any two complex numbers z1 and z2. z1 multiplied with z2 equals z2 multiplied with z1. Notice how with complex numbers, just like with regular numbers, the order in which we multiply doesn't affect the outcome. So whether we multiply z1 by z2 or z2 by z1, we always get the same complex numbers as the product. So to sum up, z1 times z2 gives us the same answer as z2 times z1. So the order of the multiplication doesn't change the product. Let's look at a specific example to see this law in action. Suppose we have two complex numbers. z1 equals 1 plus 5 times iota and z2 equals 3 minus 2 times iota. Then show the commutative law of multiplication. So let's see solution. Given that z1 equal to 1 plus 5 times iota and z2 equals 3 minus 2 times iota. So we know that if z1 equals a plus iota b and z2 equals c plus iota times d, then z1 times z2 equals ac minus bd plus iota times ad plus bc. Now z1 times z2 equals 1 times 3 minus 5 times minus 2 plus iota times 1 times minus 2 plus 5 times 3 equals 13 plus 13 times iota. Also, z2 times z1 equals 3 times 1 minus of minus 2 times 5 plus iota times minus 2 times 1 plus 3 times 5. This is equal to 13 plus 13 times iota. So this is final result. 13 plus 13 times iota is same in both cases. So the example shows the order of multiplying complex numbers doesn't change the product. Now we will discuss about associative law. For any three complex numbers z1, z2 and z3, z1 times z2 then multiply z3 equals z1 multiply with z2 times z3. When you are multiplying three or more complex numbers, then you can multiply any two of them first and then multiply the third number to that result. For example, for the complex numbers, z1 equals 1 plus 2 iota and z2 equals 3 minus iota and z3 equals minus 2 plus 4 iota. Then show the associative law of multiplication. So let's see solution. Given that z1 equals 1 plus 2 iota and z2 equals 3 minus iota and z3 equals minus 2 plus 4 times iota. So we will show that z1 times z2 multiplied with z3 equals z1 multiplied with z2 times z3. So we know that if z1 equals a plus iota b and z2 equals c plus iota d, then z1 times z2 equals ac minus bd plus iota times ad plus bc. So first multiply z1 and z2. So z1 times z2 equals 1 times 3 minus 2 times minus 1 plus 1 times minus 1 plus 2 times 3 times iota equals 5 plus 5 times iota. Now multiply z3 to z1 to times z1 into z3. So you will get z1 times z2 times z3 is minus 30 plus 10 times iota. So LHS equals minus 30 plus 10 times iota. First multiply z2 and z3. So z2 times z3 equals 3 times minus 2 plus minus of minus 1 times 4 plus 3 times 4 plus minus 1 times minus 2 times iota. This is equal to minus 2 plus 14 times iota. Now multiply z1 to z2 times z3. So then you get z1 times z2 times z3 is minus 30 plus 10 times iota. So RHS equals minus 30 plus 10 times iota. So LHS equals RHS equals minus 30 plus 10 times iota. Now we will focus on the existence of multiplicative identity. So there exists the complex number 1 plus iota times 0 denoted as 1 called the multiplicative identity, such that for every complex number z, z times 1 equals z. It means if we multiply any complex number z by 1 plus 0 times iota, then the result is just z itself. The value of z does not change. Let's look at example. So for the complex numbers, z equals to 7 minus 3 iota. So the existence of the multiplicative identity. So given that z equals 7 minus 3 times iota, so we know that if z1 equals a plus iota times b and z2 equals c plus iota times d, then z1 times z2 equals ac minus bd plus iota times ad plus bc. Now let's multiply 1 to z. So z times 1, this is simply equals to 7 minus 3 iota. As you can see, the result is still 7 minus 3 iota, which is our original complex number z. So the example shows that the multiplying 1 to a complex number does not change the complex number. So now we will discuss the existence of multiplicative inverse. So for every non-zero complex numbers z equals a plus iota times b, there exist a complex numbers z inverse such that z times z inverse equals 1, where z inverse equals a divided by a square plus b square plus iota times minus b divided by a square plus b square. Now we will see explanation. To find the inverse of z equals a plus b iota, we start with writing it as a fraction. Z inverse equals to 1 by z equals 1 divided by a plus b times iota. So we multiply both the numerator and denominator by the a minus b times iota. Then we get z inverse equals 1 divided by a minus b iota times a minus b times iota divided by a minus b times iota. This is equal to a minus b times iota divided by a square minus b iota square whole square. This is equal to a plus b times iota divided by a square minus b square times minus 1, since iota square is minus 1. So the expression for z inverse becomes z inverse equals to a plus b iota divided by a square plus b square. Finally, we can separate the real and imaginary parts of the inverse. So z inverse equals a divided by a square plus b square plus b divided by a square plus b square times iota, which we can also be written as z inverse equals a divided by a square plus b square minus plus iota times minus b divided by a square plus b square. So this matches the given formula for the multiplication inverse of a complex number. Now let's look at an example involving complex numbers. So here in this example, we have to find the multiplicative inverse of the complex number z equals 2 plus 3 iota. So given that z equals 2 plus 3 iota, so here a equals 2 and b equals 3. First calculate a square plus b square. So a square plus b square equals 2 square plus 3 square equals 4 plus 9 equals 13. Now substitute a equals 2 and b equals 3. Then a square plus b square equals 13 into the inverse of z inverse. So we get z inverse is equals a divided by a square plus b square plus iota times minus b divided by a square plus b square. This is equal to 2 upon 13 plus iota times minus 3 upon 13 equals 2 by 13 minus 3 by 13 times iota. So the multiplicative inverse of z equals 2 plus 3 iota is z inverse equals 2 by 13 minus 3 by 13 times iota. Now we will discuss the distributive law. For any three complex numbers z1, z2 and z3, z1 times z2 plus z3 equals z1 times z2 plus z1 times z3. So this law states that multiplying a complex number z1 by z2 plus z3 is equivalent to multiplying z1 by z2 and z1 by z3 separately, and then adding the resulting products. Then second distributive property, that is z1 plus z2 times z3 equals z1 times z3 plus z2 times z3. So this law states that multiplying z1 plus z2 by z3 is equivalent to multiplying z1 by z3 and z2 by z3 separately, and then adding the resulting product. So let's see here an example. So for the complex numbers, z1 equals 2 plus iota and z2 equals 1 minus 3 iota and z3 equals 4 plus 2 iota. So the distributive law of multiplication in the form z1 times z2 plus z3 equals z1 times z2 plus z1 times z3. So let's see solution. So calculating the left hand side, LHS z1 times z2 plus z3. So we know that if z1 equals a plus iota b and z2 equals c plus iota d, then z1 times z2 equals ac minus bd plus iota times ad plus bc. Also for addition, z1 plus z2 equals a plus c plus iota times b plus d. First add z1 and z3. So z1, z2 and z3. So z2 plus z3 equals 1 minus 3 iota plus 4 plus 2 iota equals 1 plus 4 plus minus 3 plus 2 times iota equals 5 minus iota. Now multiplying z1 by z2 plus z3. So z1 multiplied with z2 plus z3 equals 2 times 5 minus 1 times minus 1 plus 2 times minus 1 plus 1 times 5 times iota equals 11 plus 3 times iota. So LHS equals 11 plus 3 times iota. Now calculating the right hand side, RHS, so z1 times z2 plus z1 times z3. So we know that if z1 equals a plus iota times b and z2 equals c plus iota times d, then z1 times z2 equals ac minus bd plus iota times ad plus bc. Also for addition, z1 plus z2 equals a plus c plus iota times b plus d. So first multiply z1 and z2. So z1 times z2 equals 2 times 1 minus 1 times minus 3 plus 2 times minus 3 plus 1 times 1 times iota equals 5 minus 5 iota. Next multiply z1 and z3. z1 times z3 equals 6 plus iota times 8. Now add the two products, z1 plus z2 plus z1 into z3 equals 5 minus 5 iota plus 6 plus 8 iota. This is equal to 5 plus 6 plus minus 5 plus 8 times iota equals 11 plus 3 iota. So RHS equals 11 plus 3 iota. So since LHS equals RHS equals 11 plus 3 iota, so this verifies the distributive law of multiplication of complex numbers. Now we will discuss division of two complex numbers. So given two complex numbers z1 and z2, where z2 non-zero, the quotient z1 by z2 is defined as z1 divided by z2 equals z1 times 1 by z2 equals z1 times z2 inverse. Now problem solving method. So to simplify z1 by z2, we use a special method. We multiply both the numerator and denominator by the conjugate of the denominator. So if z equal to x plus iota times y, then conjugate of z is z bar equal to x minus iota times y of the denominator z2. Now let's let z1 equal to a plus iota b and z2 equals to c plus iota d. So z1 divided by z2 equals a plus iota b divided by c plus iota d equals a plus iota times b divided by c plus iota times d multiplied with c minus iota d divided by c minus iota d. So multiply numerator and denominator by c minus iota d. So we get Z1 divided by Z2 equals AC plus BD plus iota times BC minus AD divided by C square plus D square. Now separate into real and imaginary parts. We get Z1 divided by Z2 equals AC plus BD divided by C square plus D square plus iota times BC minus AD divided by C square plus D square. So let's look at an example. Calculate Z1 divided by Z2 for Z1 equals 3 plus 2 iota and Z2 equals 1 minus 4 times iota. So given that Z1 equals A plus iota times B equals 3 plus 2 times iota, Z2 equals C plus iota times D equals 1 minus 4 times iota. Using the formula, Z1 divided by Z2 equals AC plus BD divided by C square plus D square plus iota times BC minus AD divided by C square plus D square. Then we get Z1 divided by Z2 equals 3 times 1 plus 2 times minus 4 divided by 1 square plus minus 4 whole square plus iota times 2 times 1 minus 3 times minus 4 divided by 1 square plus minus 4 whole square. This is equal to 3 minus 8 divided by 1 plus 16 plus iota times 2 plus 12 divided by 1 plus 16 equals minus 5 divided by 17 plus iota times 14 by 17. Therefore, Z1 divided by Z2 equals minus 5 by 17 plus iota times 14 by 17. So that's all for today's lecture, and thank you very much to all of you. I hope this lesson was helpful to all of you.